them. Работает? А? Нормально, да, звук есть? Раз, раз, раз. Раз, раз. Нету? Раз, раз, раз. Так, здесь я включил. Тут я включил, да. Идет, да? А, ну отлично. Нужно начинать. И свет, наверное, давайте сразу включим. Okay, let's continue our discussion of dual pairs and weak topologies. Today our first goal will be to introduce and discuss annihilators in the general setting of dual pairs. So suppose we have a dual pair, X and Y, a dual pair of vector spaces, and suppose that M is a subset in X. We define the annihilator of M with respect to the given pairing between X and Y to be the following set. The set will be denoted like this, or more briefly like this. And it consists of those elements Y in Y, such that the pairing between X and Y is 0 for each X in M. So this is a subset in Y. And the Russian for annihilator is Annihilator. Well, here's a special case, an important special case of this notion. Suppose that X is a Hausdorff locally convex space. So we know that in this case, X and its dual, the topological dual, the space of all continuous linear functionals, form a dual pair. And we define the annihilator of a subset M in X to be the annihilator of M with respect to the pairing between X and X star. So this is a subset of X star consisting of those linear functionals, of those continuous linear functionals, which vanish at M. And duly we define the pre-annihilator of a subset M in X star to be the annihilator of M with respect to the dual pair X star X. So this is a subset in X which consists of those elements in X such that each linear functional in M vanishes at this element. In fact, we have already met these notions in the context of normed spaces. Now we discuss them in a slightly more general situation. Here are some basic properties of annihilators. So we have the following proposition. Again, we start with an arbitrary dual pair, X and Y is a dual pair. Then, first of all, if you take the zero subspace in X, then the annihilator is Y. This is clear. And if we take the whole space X, then the annihilator is 0. And this is immediate from the fact that our pairing is not degenerate. So the only element in Y which vanishes everywhere is 0. Second, if we have the following inclusion, M1 is a subset in M2, then the annihilator of M2 is contained in the annihilator of M1. This is immediate from the definition. Property 3, for each subset M in X, the annihilator of M is not just a subset of Y. This is a vector subspace, and moreover it is weakly closed. A weakly closed vector subspace of Y. And more or less for the same reason, for each subset M in X, the annihilator of M is equal to the annihilator of the weakly closed linear span of M. So if we take the linear span of M and take the weak closure, then of course this is bigger than M, but the annihilator will be the same. Well, actually there is almost nothing to prove here. 1 and 2 are absolutely trivial. And 3 follows from the fact that the annihilator of M can be interpreted as the intersection of the kernels of all elements in M. So here we interpret X, elements of X as linear functionals on Y in the standard way. So each little x is a linear functional on Y. And so this equality holds just by the definition of the annihilator. And now we recall that each x is a weakly continuous linear functional. A weakly continuous linear functional on Y. So its kernel is a weakly closed vector subspace. And of course, the intersection of weakly closed vector subspaces is again a weakly closed vector subspace. So this proves part 3. And part 4 is also true for about the same reason. Namely, each y in Y is a weakly continuous linear functional. On X. So if a little y vanishes at M, so belongs to this set, then by linearity it vanishes on the linear span, and by continuity it vanishes on the weak closure of the linear span. And so it is an element of this set. Okay, let's now introduce double annihilators. So again, we start with a dual pair, X and Y. And we define the double annihilator of a subset M in X to be the set denoted like this. And it is defined as follows. First we take the annihilator of M, and this will be a subset in Y. And then we again take the annihilator of this set with respect to the dual pair Yx, and the result will be a subset of X. And this is the double annihilator of M. So an obvious corollary of this proposition is that the following inclusion holds. The weak closure of the linear span of M is contained in the double annihilator. Well, indeed, obviously M itself is contained in the double annihilator, just by the very definition. But since the right-hand side here is a weakly closed vector subspace of X, we can take the weak closure of the linear span, and the inclusion still holds. Well, a simple but fundamental fact is that actually these spaces are the same. This is our first theorem for today, theorem 1. This is the double annihilator theorem for dual pairs. So if we start with a dual pair, xy, then for each subset M in X, the following equality holds. The weak closure of the linear span of M is equal to the double annihilator. And we also have the following closely related result. This is theorem 2. And this is the double annihilator theorem for locally convex spaces. For locally convex spaces. So suppose that X is a Hausdorff locally convex space. Then, for each subset M in X, the closure of the linear span of M is equal to the double annihilator, or more exactly to the pre-annihilator of the annihilator of M. And here the difference is that we take the closure with respect to the original topology on X, not with respect to the weak topology, but with respect to the original topology. The closure with respect to the original topology on X. I'd like to stress that theorem 2 is not a special case of theorem 1. So here we consider arbitrary dual pairs, and here we consider a concrete dual pair between X and X star. But actually, theorem 2 is not a special case of theorem 1. And the reason is that the reason is here. So we take here the closure with respect to the original topology. And we will see very soon that actually theorem 1 follows from theorem 2. So to begin with, let's prove theorem 2. So let's denote the left-hand side of this equality by x0. Let x0 denote the closure of the linear span of M. Then, first of all, we observe that the annihilator of x0 is equal to the annihilator of M. For about the same reason as here. Here we took the weak closure, but for the same reason, if you take the closure for the original topology, we still have this equality. So if a linear functional vanishes at M, then by linearity and continuity, it vanishes on the closure of the linear span. So to complete the proof, we have to show have to show that x0 is equal to the pre-annihilator of the annihilator. So obviously we have the inclusion. This subspace is contained in this one. So we have to prove the opposite inclusion. So take any element. So actually we'll show that if an element does not belong to x0, then it doesn't belong to the right-hand side. So we take an element which is not in x0. And let's recall a corollary of the Hambana theorem, namely the separation theorem for points and closed vector subspaces, which was proved some time ago. So we know that in this case, by the separation theorem, there exists a continuous linear functional on x such that f vanishes at x0, but f doesn't vanish at x. Well, now, this property means exactly that f belongs to the annihilator. F belongs to the annihilator of x0. And now, the fact that f doesn't vanish at x implies that x is not in the pre-annihilator of the annihilator. Because f is in the annihilator, so if x were in this space, then f of x would be 0. But f of x is not 0, and so x doesn't belong to this space. And actually this completes the proof. We have shown that if little x is not here, then it is not here. So this completes the proof of theorem 1, of theorem 2, And now to prove theorem 1, we simply apply theorem 2 to x equipped with the weak topology. So this is Hausdorff locally convex space, and its dual is just y. So we have proved at the previous lecture that for each dual pair, the dual of x for the weak topology is y. And so theorem 1 now implies, theorem 2 now implies this equality. So we see that actually theorem 1 is a special case of theorem 2. Okay, let's now look at some corollaries of all these results. Corollary 1, if you have a dual pair, or better, just take an arbitrary Hausdorff locally convex space, x is a Hausdorff locally convex space, and suppose that x0 is a vector subspace of x. So I claim that the closure of x0 equals the weak closure. And so in particular we see that x0 is closed in x, even only if it is weakly closed. This is actually quite surprising because in general, the weak topology is strictly weaker than the original topology. And there are many closed sets which are not weakly closed. But for vector subspaces, these two notions are the same. And the proof is immediate from theorems 1 and 2. Because, well, the closure of x0 by theorem 2 is nothing but the pure annihilator of the annihilator by theorem 2. But if we now apply theorem 1, then the same set is equal to the weak closure. And that's it. So both closures are equal to the pre-annihilator of the annihilator. In fact, this corollary can be extended to arbitrary convex subsets of X. So a convex subset of X is closed even if it is weakly closed. But the proof is more involved because it is based on a more general result on the so-called bipolar theorem. Maybe if we have time at the end of today's lecture, I'll tell you a few words about the bipolar theorem. Okay, now corollary 2. Corollary 2. Again, we suppose that X is a Hausdorff locally convex space. And suppose that M is a subset in X, and N is a subset in the dual. Then, part 1, the pre-annihilator of the annihilator of M is equal to the closure of the linear span of M and is equal to the weak closure of the linear span of M. This is just another form of writing corollary 1, actually. Because if we let x0 denote the linear span of M, then we get this equality by the double annihilator theorem. By the way, we have already discussed the first equality in the context of norm spaces. So now we see that it holds for arbitrary locally convex, Hausdorff locally convex spaces. And moreover, we can replace the closure by the weak closure, and the result is the same. Property 2, if we apply the same procedure to M, so take the annihilator of the pre-annihilator, then what we get is the weak star closure of the linear span. Of the linear span of M. In a special case where X is a norm space, we can extend part 2 as follows. So if X is a norm space, then this equality, the equality from 2, can be extended as follows. So this weak star closure contains the weak closure of the linear span and is equal to the weak closure is equal to the norm closure of M. So this is a notation for the norm closure. I suppose it is more or less self-explanatory. So the dual of X is a norm space, is also a norm space. So we can take the norm closure and the weak closure. So they are the same because of corollary 1. So these two spaces are the same. We also know that the weak star topology is weaker than the weak topology. And so we have this inclusion. And this equality holds by part 2. And finally, part 4. This is probably the best situation. If X is a reflexive Banach space, if X is a reflexive Banach space, then all spaces in its chain, well, let's denote this chain by star, all spaces in this chain are the same. So this inclusion is an equality. And this is indeed true because we have discussed some time ago that for reflexive Banach spaces, the weak topology on the dual is identical to the weak star topology. Actually, this is a characterization. A Banach space is reflexive if and only if the weak topology and the weak star topology on the dual are the same. And so in this case, we have an equality here. Corollary 3 is useful density criterion for a vector subspace. If you have a dual pair, xy, a dual pair of vector spaces, and a vector subspace x0 in X, then x0 is weakly dense. Weakly dense in X, even only if its annihilator is 0. Well, indeed, if it is weakly dense, then of course the annihilator is 0, because the annihilator of x0 is equal to the annihilator of the closure, and the closure is X itself. So the left-right implication is clear, and the right-left implication follows from the double annihilator theorem, because if this is 0, then the pre-annihilator of this is X, but the pre-annihilator of this is nothing but the closure of x0. And so x0 is dense in X, weakly dense. Corollary 4 is actually a special case of corollary 3. So now we start with a Hausdorff locally convex space. A Hausdorff locally convex space. And we take a vector subspace x0 in X and the vector subspace y0 in the dual. Vector subspaces. So part 1, x0 is dense in X, even only if it is weakly dense in X. And this happens precisely when the annihilator is 0. Well, indeed, the first equivalence holds because of corollary 1, and the second equivalence is corollary 3. Part 2 is about y0. So y0 is weakly star dense in X star, even only if its pre-annihilator is 0. I'd like to stress that for normed spaces, the weak star density here cannot be replaced by the norm density. So in general, the weak closure is strictly smaller than a weak star closure. So it can happen that a subspace of the dual of a normed space is not dense, is not norm dense, but is weakly star dense. And in fact, this is typical. This is typical because of the following useful exercise. If X is any non-reflexive Banach space, a non-reflexive Banach space, then there exists a norm closed and weakly star dense proper vector subspace of the dual y0 in the dual. So it is a proper vector subspace which is norm closed but which is weakly star dense. So this phenomenon is typical. We can find such a subspace for any non-reflexive monospace. But of course, for reflexive monospaces, this never happens because the norm closure, the weak closure, and the weak star closure in the dual are identical. Corollary 6. Oh, sorry, Corollary 5. Corollary 5. Corollary 5. If X is any normed space, then the canonical image of X in the bidual is weakly star dense. Canonical image of X in the bidual is weakly star dense. So we know that it is always closed. So the canonical, if X is in Barnard space, then the canonical embedding is an isometry. So the canonical image of X in the bidual is a closed vector subspace. So it is closed, but it is always weakly star dense. And the proof is again immediate from the double annihilator theorem. So because if we identify X with its canonical image in the bidual and consider the dual pair X double star and X star, this is a dual pair, then the annihilator of X, so X sits in the bidual, its annihilator sits in X. Its annihilator sits in the dual in X star, but this is 0. This is 0 because, well, if a linear functional vanishes everywhere on X, then it is 0. This is a tautology. And so this is 0, but this means exactly by corollary 3. So we apply corollary 3 to this dual pair, and we see that X is weakly is dense in X double star for this topology. So by corollary 3, X is weakly star dense in the bidual. Corollary 6 is about linear operators. Suppose I have two Hausdorff-locally convex spaces, X and Y, and suppose that T is a continuous linear operator. T is a continuous linear operator from X to Y. Then we have the following inequalities. First of all, the kernel of the dual operator, T star, is equal to the annihilator of the image of T. Second, the pre-annihilator of the kernel of T star is equal to the closure of the image of T and is equal to the weak closure of the image of T. Equality 3 is a dual to 1. So the kernel of T is equal to the pre-annihilator of the image of T star. And finally, the annihilator of the kernel of T is equal to the weak star closure of the image of T star. Well, some parts of this result were already proved earlier for normal spaces, but some of them are new. For example, so far, we didn't know what exactly is the annihilator of the kernel. So in the context of norm spaces, we knew only that the annihilator of the kernel contains the norm closure of the image of T star. And now we know exactly that this annihilator is equal to the, not to the norm closure, but to the weak star closure of the image of T star, which is in general strictly bigger than the norm closure. Well, the proof of the first equality is immediate and is exactly the same as in the context of norm spaces. Namely, a linear functional f belongs to the kernel of T star, that is, T star of f is 0, even only if the composition of f and t is 0. But this means exactly that f sits in the annihilator of the image of T. Part 2 follows from part 1 if we take the pre-annihilators here. So the pre-annihilator of this is equal to the pre-annihilator of this. And now one of our previous corollaries, corollary 2, implies that this is nothing but closure or equivalently the weak closure of the image of T. So 2 follows from 1. And from corollary 2. And now to prove 3 and 4, so the easiest way to prove 3 and 4 is to observe that we can just take the dual operator and consider it as an operator between the weak star, the duals equipped with the weak star topologies. So we apply 1 and 2 to the dual operator, which acts from y star to x star, and both the duals are equipped with the weak star topologies. So if we apply 1 and 2 to T star, what we get is exactly 3 and 4 respectively. And finally, a useful special case of corollary 6 is the following injectivity criterion. The following injectivity criterion for linear operators, corollary 7. So again, we suppose that x and y are Hausdorff locally convex spaces, and T is a continuous linear operator from x to y. Then T star is injective if and only if the image of T is dense in Y. And this happens if and only if it is weakly dense. It is weakly dense in Y. Well, indeed, T star is injective if and only if this is 0. That is, if and only if the annihilator of the image of T is 0, but we know that the annihilator is 0, if and only if the subspace is dense, or equivalently weakly dense by corollary 1. And similarly, T is injective even only if the image of T star is weakly star dense. In X star. And similarly, this follows from part 4 of corollary 6. Again, I'd like to stress that we knew that effects in Y norm spaces, then we already know that if the image of T star is norm dense, then T is injective. And we also have some examples which show that this is not an equivalence. So now to get the equivalence, we simply replace the norm density by the weak star density. And we get an equivalence. So T is injective if and only if the image of T star is weakly star dense. Okay, now our next goal is to prove an important result, which is usually referred to as the Banach-Alaoglu-Bourbaki theorem. Some people call it the Banach-Alaoglu theorem. Some people call it the Alaoglu-Bourbaki theorem. So maybe let's mention Banach, Alaoglu, and Bourbaki. This is more or less correct for historical reasons. We start with the following definition. Suppose that X and Y are topological vector spaces, and suppose that M is a subset in the space of continuous linear operators from X to Y. We say that M is equicontinuous if for each neighborhood of 0 in Y, there exists a neighborhood of 0 U in X, such that each operator from M takes U to V. For each T in M, we have the following inclusion. So the Russian for equicontinuous is равностепенно непрерывно. Ну, иногда еще говорят эквинепрерывно, но это реже. So if we write this property for a single operator, so if M consists of a single operator, this is just the continuity at 0. But we know that a linear operator is continuous even only if it is continuous at 0. So for a single continuous linear operator, this property always holds. So here the point is that we can find the same U for all operators in M. So this shows that this is stronger than the continuity of each individual operator from M. So the difference is that U, the same U, works for all operators in M. Here's a useful example and an exercise in the same time. Suppose that X and Y are norm spaces. Then a subset in the space of all continuous linear operators is equicontinuous, even only if it is bounded with respect to the operator norm on this space. It is bounded with respect to the operator norm. This is more or less immediate from the definition. So it suffices to check this condition only in the case where is a unit ball in Y. So U will be an open ball of radius epsilon. And this inclusion means that each operator from M, the norm of each operator in M, is less than or equal to 1 over epsilon. That is, M is bounded. So now we have the following theorem. It's called Theorem 1. The Banach-Aloglu and Bourbaki theorem. In this context, Bourbaki usually means Dieudonné and Schwarz. So of the whole Bourbaki group, only Dieudonné and Schwarz worked with topological vector spaces, and later Grothendieck. But this was a bit earlier. This result was obtained in the 1940s. So suppose that X is an arbitrary topological vector space, and M is an equicontinuous subset of the dual. An equicontinuous subset of the dual. Then M is relatively weakly star compact. In the dual. Relatively means that its closure in the dual is weakly star compact. So this is a very important result, actually of about the same importance as, for example, the Hambana theorem, or the open mapping theorem, or the Banach-Steinhaus theorem. So this is one of the most fundamental results of the classical functional analysis. So to prove this result, we look at the dual, and we consider the dual as a vector subspace in the space of all k-valued functions on X. Here is usual bold k denotes the base field, which can be either the field of real numbers or the field of complex numbers. And let's observe that the weak star topology on the dual is nothing but the restriction to the dual of the product topology on k to the power x. So if you recall the definition of the product topology, you can also recall that it is given by a family of seminars. We will see that indeed the induced topology on X star is nothing but the weak star topology. Okay, now to prove the result, it suffices to prove the following two statements. So let now M bar denote the closure of M in k to the power x. So we take the closure, for convenience, we take the closure not in this space, but in the whole space of all functions on x. So to compute the proof, it suffices to show that first, M bar is compact, and second, M bar is contained in X star. So the combination of 1 and 2 shows that M bar is identical to the closure of M in X star, and so it is relatively compact in X star. Okay, let's start with part 1. Why is it compact? Of course, we use the assumption that M is equicontinuous. So by assumption, there is a neighborhood of 0, say U in X, such that for each F in M and for each little u in U, I have the following inequality. Just by the equicontinuity of M. Now, for each x in X, let Mx denote the image of M under the respective projection to K. That is, this is the set of all elements of the form f of x, where f runs over M. So this is a subset in K. Subset in K. I claim that Mx is bounded. Why is it so? Let's observe that for each x in X, you can always find a positive number lambda such that lambda x belongs to U. This is true because by the continuity of multiplication by scalars. So if lambda goes to zero, then lambda x goes to 0. So if lambda is small enough, then lambda x will be will belong to an arbitrary neighborhood of 0. So this follows from the continuity of the map which takes lambda to lambda x. Now, if we take any element f in M, so f of lambda x, because of this, f of lambda x is less than or equal to 1, and so f of x is less than or equal to 1 over lambda. And this implies that Mx is bounded. And now to complete the proof of part 1, we use Tiganov's theorem. Well, indeed, by the construction of Mx, we have the following conclusion. This is true by construction. So the closure of M is contained in the product of the closures of Mx. But each Mx is bounded, so its closure is compact in K, and the product of compact spaces is compact by Tiganov's theorem. So M bar is compact because it is a closed subset of a compact space. M bar is compact. Okay, this completes the proof of part 1. And now we have to show that actually this set and closure, so we're taking closure in K to the power x, but actually this set consists of continuous linear functionals. Why is it so? First of all, if we take any two elements x and y and x, and any two numbers alpha and beta, we can consider the following map. The map from K to the power x to K, which takes f to f of alpha x plus beta y minus alpha f of x minus beta f of y. And let's observe that this map is continuous on K to the power x. It is continuous because we have here 3 evaluation maps, and each evaluation map is continuous, and of course a linear combination of continuous functions is continuous. So this function is continuous, and of course it vanishes on M, because M consists of linear functionals. It vanishes at M. So by linearity, by continuity, it vanishes at M bar. By continuity. But this means exactly that M bar consists of linear functionals. And bar is contained in, well, in our notation, this is x hash, the space of all linear functionals on x. So each element in M bar is a linear functional. And finally, we have to show that each element in here is continuous. Well, again, we come back to the equicontinuity assumption. So we will now use this assumption once again. Let's now look at the following set. The set which consists of all those elements, all those functions on x, for which this property holds. For each little u in u, the absolute value of f of u is less than or equal to 1. So what can we say about this set? Let's observe that this set is closed in k to the power x. It is closed because, well, if for each individual u, this is the evaluation map is continuous for the product topology, and the intersection of closed sets is closed. So it is closed, but on the other hand, it contains M by assumption. It contains M. So therefore, it contains the closure of M. So we see that this property holds for each f in the closure of M. But this is just a continuity. So we now take any positive epsilon. And any element, say v, in epsilon u. So epsilon u is also neighborhood of 0. So then we have, by linearity, we have the following inequality. This is less than or equal to epsilon. And since epsilon is arbitrary and epsilon u is a neighborhood of 0, we conclude that f is continuous. Well, we prove that f is continuous at 0, but since f is linear, it is continuous everywhere. And so this implies that, and this is true for any f. Sorry, I forgot to say. This holds for any f in M bar. For any f in M bar. And so this implies that M bar is actually contained in X star. And this completes the proof. So let me stress once again that we have used the equicontinuity assumption twice. First, we used the equicontinuity assumption here to show that each projection Mx is bounded, and the second instance is here. Okay. Our next result, theorem 2, is actually a refinement of theorem 1 in a special case where X is separable. Suppose that X is a separable topological vector space. X is a separable topological vector space, and M is an equicontinuous subset of X star. When I claim that M is not only relatively compact, but is also metrizable. Metrizable and relatively compact in X star with respect to the weak star topology. I'll give you only a sketch of proof. Actually, the proof will be reduced to a couple of simple but useful exercises. Well, since X is separable, we can choose a countable dense subset. Let's denote the elements of the set by xn, where n runs over the natural numbers. And countable dense subset of X. And we introduce a countable family of seminorms on X star, as denoted by P. The seminorms will be denoted by will be indexed by natural numbers. And the f seminorm at f, where f is linear functional, will be just the absolute value of f of xn. So we obtain a countable family of seminorms on the dual. So exercise 1. The topology determined by P is metrizable. Actually, this is one of the exercises in exercise sheet 3. A local economics topology determined by a countable family of seminorms is metrizable. And the second exercise, if we look at the topology tau of P and at the weak star topology, I don't claim that they are identical. In general, this is not the case. But I claim that they induce the same topology on M. Induce the same topology on M. If we consider them on the whole space X star, then the weak star topology will be stronger, because in the weak star topology we consider the absolute values of f of x for all elements in X. And here we take only the countable dense subset. So in general, tau of P is weaker than the weak star topology, but they are identical on M. Of course, here the equicontinuous assumption is essential. So modulo these exercises, theorem 2 becomes is reduced to theorem 1, because it is M is relatively compact for the weak star topology by theorem 1, and it is metrizable because of these exercises. Here's an important special case, a corollary. Suppose that X is norm space. Then the closed unit ball of the dual, is a weakly star compact. By the way, let's recall that if X is infinite dimensional, then the unit ball is never compact for the norm topology. It is never compact for the norm topology, but we see now that it is weakly star compact. And this indeed follows from theorem 1. By theorem 1, it is, the open unit ball, the closed unit ball in X is, of course, in X star is, of course, equicontinuous, because it is norm bounded. So it is a relatively weak star compact, but on the other hand, it is very easy to show that it is weakly star closed. It is weakly star closed, so it is weakly star compact. And second, if X is separable, then the closed unit ball in the dual is weakly star metrizable and weakly star compact. So as a corollary, it is weakly star sequentially compact. we know that each metrizable, for metrizable spaces, compactness and sequential compactness are equivalent. So since this space is metrizable, we conclude that it is sequentially weakly star compact. And historically, this is the first statement of this result, proved by Banach in 1929. So actually what Banach proved is that if you have a separable norm space, then each norm-bounded sequence in the dual has a weakly star convergent subsequence. So in other words, this space is set as sequentially weakly star compact. And the proof given by Banach was different. It used some kind of diagonal process. And this is not surprising because Tiganov's theorem was not available in 1929. It was proved only in the 1930s. And after Tiganov's theorem was published, very quickly, Aloglu and independently Bourbaki observed that that this result holds for an arbitrary equicontinuous subset of the dual of a topological vector space. So the proof we gave today is independently due to Aloglu and Bourbaki. This, if I'm not mistaken, this is 1938. Okay. We still have some time. Well, let me now say a few words about polars. I briefly mentioned that some results which we proved today for vector subspaces are also true for convex sets. And this follows from another fundamental result which generalizes the double annihilator theorem, the so-called bipolar theorem. A few words about polars. So again, we consider an arbitrary, first of all, we take an arbitrary vector space. X is a vector space, as usual, over the field of real numbers or the field of complex numbers. Now let's recall the following definition. We say that a subset M in X is absolutely convex. Absolutely convex if for each finite family of elements xn, x1, xn in M, and for each family of numbers, lambda 1 to lambda m, such that the sum of their absolute values is less than or equal to 1, we have the following conclusion. The linear combination of our elements belongs to M. So it's a simple exercise to show that M is absolutely convex, even only if it is convex, and is stable under multiplication by numbers of modules less than or equal to 1. So we have the following conclusion: whenever the absolute value of lambda is less than or equal to 1. We can define the so-called absolutely convex whole of M as follows. Absolutely convex whole of M to be the following set. Usually it is denoted by gamma of M, and it consists of all linear combinations of this form. So we consider all linear combinations where lambda I are in K, xi belong to M, and the sum of the absolute values of these numbers is less than or equal to 1. And it's a simple exercise to show that the absolutely convex whole is the smallest absolutely convex set containing M. Okay, let's now introduce the notion of a polar with respect to any dual pair. So we take an arbitrary dual pair, x and y, a dual pair of vector spaces, and we take a subset M in X. We define the polar of M with respect to this dual pair to be the following set, which will be noted by M little circle. And by definition, it consists of those elements in Y such that the absolute value of the pairing between X and Y is less than or equal to 1. And this holds for each X in M. The Russian for polar is поляра. По-русски она женского рода. Well, what can we say about this notion? First of all, it easily follows from the definition that the polar of any set is an absolutely convex. Is absolutely convex and weakly star closed. Weakly closed subset of Y. Absolutely convex and weakly closed. This is more or less immediate from the definition. The absolute convexity is immediate from the definition, and the weak closedness follows from the fact that each little x is continuous, is weakly continuous on Y. And the second useful observation is that there is a close relation between polars and annihilators. Well, indeed, actually, the annihilator of M is nothing but the polar of the following set. So we multiply the elements in M by arbitrary natural numbers, and then take the polar. Take the polar. Or equivalently, we can take the linear span of M, and then take the polar. Why is it so? Well, indeed, if you take an element in here, an element in this polar, so we have this inequality for each x in this set. So if x is in M, then n, we can substitute here n multiplied by x. And so after we divide by n, we see that this number is less than or equal to 1 over n. for each n. So this happens for each n if and only if this is 0. That is, if and only if little y sits in the annihilator. So this is a relation between polars and annihilators. And in particular, we see that if M is a vector subspace, if M is a vector subspace, of X, then the polar and the annihilator are the same. By the way, here's a typical example of a polar. A typical example. If X is a norm space, we can take the closed unit ball in X. Then the polar of the closed unit ball with respect to the duality between X and X star is nothing but the the closed unit ball in the dual. Closed unit ball in the dual. And what happens if we take the closed ball of radius r? And the polar will be the closed ball of radius 1 over r. It's a simple exercise. So we have the following result. This is the so-called bipolar theorem for dual pairs. Theorem 1. If we take any dual pair, x and y, dual pair, and a non-empty subset M of X, an arbitrary non-empty subset, then the bipolar of M, so I forgot to say what a bipolar is, but it's more or less immediate from the title. Bipolar is the polar of the polar. And the bipolar is equal to the weak quarter of the absolutely convex whole of M. So the bipolar is the polar of the polar. In Russian, bipolar. So the bipolar is equal to the weak closure of the absolutely convex whole. And this extends the double annihilator theorem for dual pairs because of this observation. So if we apply this to the linear span of M, what we get is exactly the double annihilator theorem. And we have a similar result, theorem 2, for locally convex spaces. The bipolar theorem for locally convex spaces. If X is a Hausdorff locally convex space, and M is a non-empty subset of X, then the bipolar of M is equal to the closure of gamma of M for the original topology on X. Here we take the closure with respect to the original topology. The proof of the bipolar theorem is slightly more involved than the proof of the double annihilator theorem, so I have no time to prove this result. But it is also based on the Hahn-Banach theorem. Again, the main technical tool is the Hahn-Banach theorem. So as a corollary, we see that if X is a Hausdorff locally convex space and M is an absolutely convex subset, then the closure of M is equal to the weak closure of M. So in particular, M is closed if and only if it is weakly closed. And moreover, there is another modification. If we suitably modify the bipolar theorem, then we can show that this corollary is true for all convex subsets of M, of X. Not necessarily absolutely convex, but also for convex subsets. Another useful corollary is the so-called Goldstein's theorem. If X is an ordinate space, then the closed unit ball of X is weakly star dense in the closed unit ball of the bidual. So to prove this corollary, we simply apply the bipolar theorem to the canonical image of the unit ball in the bidual. So its bipolar will be the closed unit ball of the bidual, and so it follows that it is the ball itself is weakly star dense in the ball of the bidual. And this is, by the way, this is stronger than what we have proved before. So some time ago, today we proved that X itself is weakly star dense in the bidual. And this is stronger because here we have a control on the norms. So if we take a point in here, then we knew before that this element in here can be approximated in the weak star topology by elements in X. So Goldstein's theorem says that actually it can be approximated by elements in the unit ball of X, which is stronger. And finally, if we combine this with the Banach-Haloglu theorem, we get another corollary. If X is a Banach space, then X is reflexive if and only if its unit ball is weakly compact. Well, indeed, the left-right implication follows from the Banach-Haloglu theorem. If it is reflexive, then we can identify this ball with the unit ball in the bidual. So the weak topology and the weak star topology on the bidual are identical. And so everything follows from the Banach-Haloglu theorem. And the right-to-left implication follows from Goldstein theorem. Because if X is not reflexive, then this ball is a proper dense subset in here. A proper dense subset. So it is never compact, because a compact space is closed everywhere in any bigger space. So it is not closed in here, and so it is not compact. Okay, so that's all for today. And more or less that's all I wanted to tell you about topological vector spaces. So at the next lecture, we begin to discuss Gelfand's theory for commutative Banach algebras. So our final goal will be to apply the theory of commutative Banach algebras to spectral theory of linear operators on the Hilbert space.